The thermometer read 12 degrees below zero outside Henrik Larsson's cabin, but in the sleeping loft 20 feet above his fireplace, the air held steady at 73 degrees, while his neighbors 3 miles away burned twice the firewood and still woke shivering at dawn. What happened in the 18 months before that January night in 1843 would change how frontier families survived winter across the Northern Territories. But the innovation that made it possible began with a death that no amount of firewood could have prevented. Before we go further, drop a comment letting us know where you're watching from. And if survival ingenuity like this fascinates you, hit that subscribe button, because tomorrow's story involves an engineering solution even more unexpected than this one. The fire had burned all night. Henrik Larsson had made certain of that, feeding split pine into the stone fireplace every time he woke, which was often in the brutal cold of January. 1842. The cabin held heat poorly despite his best efforts. 3 feet from the flames, you could feel genuine warmth. 6 feet away, your breath formed clouds. At the far wall, where his trapping partner, Olaf Bergman, slept on a raised platform, the temperature barely climbed above freezing, even with the fire roaring. Henrik had known this was a problem. Every mountain man knew it. Single-room cabins were either unbearably hot near the fire or dangerously cold everywhere else. You chose your misery and accepted it as the cost of frontier life. But on the morning of January 14th, acceptance stopped being enough. Henrik woke at first light and immediately knew something was wrong. The silence was too complete. Olaf was a restless sleeper who coughed frequently, a consequence of nearly drowning in an icy stream the previous winter. The absence of sound pulled Henrik fully awake. He left his own sleeping platform near the fireplace and crossed the cabin. Olaf lay, motionless under 3 layers of blankets and a bearskin. Henrik touched his face and pulled his hand back from the cold flesh. Olaf Bergman had frozen to death 15 feet from a fire that had burned throughout the entire night. The impossibility of it struck Henrik with physical force. He had kept the fire going. He had done everything right. The cabin walls were chinked properly. The door fit tightly. The roof didn't leak. By every standard of frontier construction, this was a solid shelter. Yet a man had died of cold inside it, while heat poured from the fireplace not 20 feet away. Henrik stood there for long minutes, trying to understand how this could happen. The fire had been large enough that he'd been comfortable in his sleeping spot near the hearth. But Olaf, sleeping farther away to avoid the excessive heat that made sleeping near the fire uncomfortable, had been too far from the warmth to survive. The mathematics were simple and brutal. Heat traveled in straight lines from the source. The farther you moved from the fire, the less heat reached you. Cabin walls reflected some warmth back into the room, but most of the heat simply rose straight up and escaped through the roof or distributed so weakly across the space that it became useless for warming anyone not directly in front of the flames. Every trapper knew this. Every settler accepted it. You either slept too hot or too cold. There was no middle ground in a single level cabin. Henrik prepared Olaf's body as best he could in the frozen conditions. He wrapped him in the blankets that had failed to save him and secured the bundle with rope. The ground outside was frozen solid, too hard for immediate burial. He would have to wait for a thaw or build a fire to soften the earth. For now, he placed Olaf's body in the small lean-to, attached to the cabin where supplies were stored. The cold would preserve him until proper burial became possible. Henrik spent the rest of that day observing his cabin with new attention. He fed the fire and watched how the heat behaved. The warmth rose immediately from the flames, traveling straight upward toward the roof. He could feel it intensely if he held his hand above the fireplace, but that heat dissipated somewhere between the fire and the ceiling. It didn't accumulate. It didn't collect anywhere useful. It simply vanished into the logs and thatch above, wasted on empty space while the far corners of the cabin remained cold enough to freeze a man. He moved methodically around the single room, noting temperatures by feel. Directly in front of the fireplace, the heat was almost unbearable. 3 feet to either side, it dropped to merely warm. 6 feet away, it became cool. At the walls farthest from the fire, ice crystals formed on the interior surface of the logs, despite the roaring flames 15 feet away. The pattern was consistent and predictable. Heat radiated outward from the source, but weakened dramatically with distance. More importantly, heat rose. He confirmed this by climbing onto his sleeping platform and feeling the air near the ceiling. It was noticeably warmer 8 feet above the floor than at ground level, yet still not warm enough to matter, because the heat escaped through the roof almost as quickly as it rose. Henrik had no formal education in physics. He had learned reading and basic mathematics from his father in Norway before immigrating to America at age 19. He knew carpentry and stonework from apprenticing with his uncle. His understanding of heat came purely from observation and experience. But standing in his cabin that January afternoon, watching his breath form clouds while a massive fire burned uselessly nearby, he began to grasp something fundamental. Heat wanted to rise. If you could capture it as it rose, if you could collect it somewhere instead of letting it escape, you could create warmth where you needed it without requiring the massive fires that most trappers burned. Through winter nights, the idea formed slowly. What if the cabin had levels? Not separate rooms, but vertical layers within the same structure. The fire could burn at a middle height. The heat would rise naturally. If there was an upper level where that heat collected, instead of escaping through the roof, that upper level would be warm. The middle level where the fire burned would be comfortable. And if there was a lower level below the fire, it would stay cool naturally. 3 different temperatures in one structure, all created by letting heat do what it naturally wanted to do. Other trappers would think he was insane. He knew that already. Building multiple levels inside a cabin made no sense by conventional wisdom. Why build stairs when you could simply walk across a single floor? Why waste lumber creating separate levels when a single room could hold everything a man needed? But conventional wisdom had let Olaf freeze to death 20 feet from a fire. Henrik was done with. Conventional wisdom. He needed to understand if his idea could actually work. The thaw came 6 days later. Henrik spent those days preparing the gravesite on a small rise 50 yards from the cabin. He built fires on the frozen ground, letting them burn for hours to soften the earth enough for digging. The work was slow and physically brutal. Each fire heated perhaps 6 inches of soil. He would scrape away the softened earth, build another fire, and repeat. It took 3 full days to dig a grave deep enough. Olaf had been a good partner, careful with supplies and reliable on the trap lines. He deserved proper depth. On the morning of January 20th, Henrik carried Olaf's frozen body up the rise and lowered it into the grave. There were no other trappers nearby to help with the burial or speak words over the grave. Henrik stood alone in the bitter cold and tried to think of something appropriate to say. He wasn't a religious man, but the moment seemed to require acknowledgement. Finally, he simply said, "You deserved better than freezing in your sleep," and began filling the grave. The dirt was still partially frozen and fell into the hole with hollow sounds that seemed too final. After the burial, Henrik returned to the cabin and made a decision that would consume the next 18 months of his life. He would solve the problem that had killed Olaf. He would figure out how to keep a cabin warm enough to prevent death without requiring a man to sleep so close to the fire that comfort became impossible. The idea of vertical levels, of capturing rising heat in an upper chamber while maintaining comfort below, had taken hold in his mind. It seemed possible. It seemed logical, but he had no idea if he could actually build it. That evening he began sketching plans using charcoal on pieces of birch bark. His drawings were crude, but they captured the essential concept. A structure with 3 distinct levels. A bottom level that would serve as cold storage, staying naturally cool through earth contact. A middle level with the fireplace where living and working would happen. An upper level beneath the roof where heat would collect and create a warm sleeping space. He calculated roughly how much lumber he would need, how deep he would need to dig for the lower level, and how he would support the weight of multiple floors. The numbers were daunting. Other trappers visited occasionally, traveling through the area on their way to trading posts or checking distant trap lines. When they saw Henrik's sketches and heard his plans, their reactions ranged from confusion to outright mockery. One trapper, a grizzled Scotsman named Douglas, looked at the drawings and laughed so hard he had to sit down. "You're going to build stairs inside your cabin? Stairs to go from one side of a room to the other?" Douglas shook his head. "Grief's made you strange, Henrik. Just build a normal cabin like everyone else." Henrik left the mountains in early March when the trap lines became less productive. Most trappers used this time to travel to settlements, sell their furs, resupply, and occasionally remember what civilization felt like. Henrik had different priorities. He spent 3 weeks traveling to every settlement within reasonable distance, studying buildings with multiple floors. In a trading post in Fort Union, he stood for hours watching how heat moved through a 2-story structure. The upper floor stayed noticeably warmer than the lower floor, even though the stove was on the ground level. The heat rose naturally and collected in the upper rooms. He examined construction techniques, paying particular attention to how floors were supported. Large wooden beams called joists spanned the width of buildings, resting on load-bearing walls or pillars. Planks laid across these joists created the floor surface for the upper level and the ceiling for the lower level. The system was simple in concept but required precision in execution. The joists had to be strong enough to support the weight of floors, furniture, and people. They had to be spaced correctly to prevent sagging, and they had to be secured properly to prevent structural failure. In a small settlement near the Yellowstone River, Henrik found a 2-story house where the owner, a carpenter from Pennsylvania, was willing to answer questions. The carpenter explained load distribution, how weight transferred through joists to supporting structures. He described the importance of cross-bracing to prevent lateral movement. He showed Henrik how to calculate the strength needed for different span lengths based on the wood type and dimensions. The information was technical and detailed, far beyond anything Henrik had learned during his carpentry apprenticeship. But he absorbed it all, asking questions until the carpenter grew tired of answering. Henrik also studied stone construction wherever he found it: fireplaces, foundation walls, support pillars. He learned that stone could bear enormous weight if properly stacked and mortared. He observed how stonemasons selected rocks for different purposes, using larger flat stones for load-bearing foundations and smaller stones with mortar for walls that didn't carry significant weight. The principles were straightforward but required skill to execute properly. Stone had to be fitted carefully to distribute weight evenly. Mortar had to be mixed to the right consistency and applied correctly, or the structure would fail. By late March, Henrik had filled his mind with construction knowledge that most trappers never bothered learning. He understood floor systems, load-bearing calculations, stone masonry techniques, and thermal properties of different materials. He knew how to build what he envisioned. The question was whether he had the skill and determination to actually do it alone. Building a multi-level structure wasn't something one man typically attempted. It required help, multiple workers, and considerable time. But Henrik had no partners after Olaf's death, and he wasn't interested in explaining his plans to skeptical trappers who would only slow him down with doubts. Henrik returned to his trapping territory in April with a wagon full of supplies that raised eyebrows at every trading post along the route. He had purchased 40 feet of chain, 6 iron brackets designed for heavy beam support, a collection of specialized stoneworking tools, and more nails than most trappers used in 5 years. He had also acquired 3 long iron rods, each 6 feet in length and an inch thick, that weighed so much the trader had questioned whether Henrik understood how difficult they would be to transport. Henrik understood perfectly. Those rods would pin his floor joists to stone pillars, creating connections that could support the weight of everything he planned to build above them. Word spread quickly through the scattered trapping community. Trappers talked during chance encounters on trails or at seasonal camps. By May, everyone within 50 miles knew that Henrik Larsson was planning to build something strange. When trappers stopped by his camp to see for themselves, Henrik showed them his detailed plans drawn on birch bark and explained his reasoning about thermal stratification. The reactions were consistently negative, though they varied in tone from concerned to contemptuous. A French-Canadian trapper named Baptiste thought Henrik had lost his mind from grief. "You want to dig a hole under your cabin and then build floors inside with stairs? Mon ami, this is madness. Just sleep closer to the fire like normal men." Henrik tried to explain about temperature zones and capturing rising heat, but Baptiste shook his head and left, convinced Henrik needed rest more than he needed construction projects. An American trapper from Ohio was more direct in his assessment. "You're going to spend all summer building stairs so you can walk up and down inside your own cabin? Hell, Henrik, most of us just turn around if we need to face the other direction." The mockery stung, but Henrik expected it. Revolutionary ideas always faced resistance from people invested in conventional methods. What bothered him more was when trappers questioned the basic physics of his plan. A Norwegian trapper named Knut, who Henrik respected for his survival skills, raised concerns about the heating concept itself. Heat rises, yeah, but it doesn't stay risen. It escapes through the roof. You build an upper floor, that floor will be cold like everywhere else far from the fire. You're just making more cold space to heat. Henrik tried to explain that the upper level would be enclosed, trapping the heat that rose into it, but Knut remained skeptical. Douglas, the Scottish trapper, who had laughed at Henrik's initial sketches, returned in June with 3 other trappers specifically to see if Henrik was actually proceeding with his absurd plan. When they found Henrik digging a pit where his cabin would stand, excavating several feet below ground level, Douglas addressed the assembled group as if Henrik couldn't hear him. "Look at him, building himself a grave. That's what comes from spending too much time alone after your partner dies. Man starts digging holes and calling it innovation." The other trappers laughed, and Douglas called out to Henrik directly, "When you finish burying yourself, let us know. We'll come fill it in properly." The excavation took 3 weeks of brutal physical labor. Henrik marked out a rectangle 16 feet by 20 feet, larger than most single-room cabins, but necessary for his 3-level design. He needed space for stairs, for multiple functional areas, and for proper heat circulation. He began digging in early June when the ground had thawed enough to make excavation possible. The first foot of soil came out relatively easily, mostly dirt and small rocks that he could remove with a shovel. Below that, the composition changed to rocky clay, packed so tightly it required a pickaxe to break apart. Henrik worked methodically, loosening soil with the pickaxe, then shoveling it out, then loosening more. He hauled the excavated material away from the cabin site, spreading it in areas where the ground was uneven. The physical demands were exhausting. His hands blistered, then calloused. His back ached constantly from the repetitive motion of swinging the pickaxe and lifting shovel loads of rocky soil. But he continued, because every inch of depth he achieved, it created more thermal mass and better insulation for his lower level. That lower level would serve as cold storage, and the deeper it sat, the more effective it would be. By the 3rd day, he had reached 2 feet of depth across the entire rectangle. He kept digging. 3 feet down, he hit a layer of stones ranging from fist-sized to as large as his head. These weren't scattered rocks, but a continuous layer that seemed to extend across much of the excavation. Henrik worked around the largest stones where possible, digging out the soil between them. When he encountered stones too large to work around, he used iron wedges and a sledgehammer to crack them into manageable pieces. The work was slow and dangerous. A poorly struck wedge could send stone fragments flying. A misplaced sledgehammer swing could shatter his hand. 4 feet down, the excavation looked less like a building site and more like a deliberate pit. When trappers passed by and saw how deep Henrik had gone, their mockery intensified. One trapper brought friends specifically to show them the fool digging to China. They stood at the edge of the pit watching Henrik work, making jokes about whether he planned to trap beavers underground. Henrik ignored them and kept digging. He had calculated that 4.5 feet of depth would give him adequate headroom in the lower level, after he added stone walls and a floor system above. He needed 6 more inches. The final 6 inches took 4 days to complete because he encountered bedrock in several areas. Where he couldn't dig deeper, he used his pickaxe to chip away at the stone surface, creating a level floor plane across the entire excavation. When he finally climbed out of the completed pit in late June, filthy and exhausted, he stood at the edge and looked at what he had accomplished. The rectangular hole measured 16 feet by 20 feet and averaged 4.5 feet deep. It looked like a grave for a giant, exactly as Douglas had predicted. But Henrik saw something different. He saw the foundation of a thermal system that would revolutionize how frontier cabins handled heat. The stonework began in early July. Henrik needed to build support pillars inside the excavated pit that would carry the weight of the middle floor and everything above it. He had planned for 6 pillars arranged in 2 rows of 3, creating a grid pattern that would distribute weight evenly across the structure. Each pillar would rise from the bottom of the pit to just below ground level, where they would support the massive joists that would carry the middle floor. The physics were straightforward. 6 pillars meant each would carry approximately 1/6 of the total weight from floors, walls, roof, furniture, stored supplies, and Henrik himself moving around the upper levels. He spent 3 days gathering stones suitable for pillar construction. He needed large, relatively flat stones for the base of each pillar, then progressively smaller stones as the pillars rose. He found most of his materials in a rocky area a 1/4 mile from the cabin site, where an ancient stream bed had deposited stones of every size. He hauled them back using a simple sledge made from poles and rawhide, dragging loads that sometimes weighed over 200 pounds. His initial estimate had been that he would need approximately 800 stones total for all 6 pillars. By the time he finished gathering, he had collected nearly 1,000, giving himself extra materials in case his pillar building went poorly. The mortar was a mixture he had learned about during his settlement visits. 3 parts sand to 1 part lime, with water added until the consistency felt right. He had purchased lime in Fort Union specifically for this purpose, hauling the 50-pound sack across 100 miles of wilderness. Most trappers would have considered this insane. Lime was expensive and heavy, but Henrik knew that mortar was what would make his pillar strong enough to support thousands of pounds without settling or cracking. Mud and clay would fail eventually. Proper lime mortar would last decades. He began the first pillar on July 8th. The base stones were critical. He selected the largest, flattest stones from his collection and fitted them together in the bottom of the pit, creating a foundation approximately 2 feet square. He used mortar sparingly at this level because the weight from above would compress everything together naturally. The real importance of mortar came in the upper sections where stones needed adhesive strength to maintain position. He built slowly, adding 1 course of stones at a time, letting each level set for several hours before adding the next. Each pillar required different stone selections as it rose because the dimensions changed. The bases were broader for stability. As the pillars gained height, Henrik tapered them slightly, reducing the footprint while maintaining structural strength. This wasn't just aesthetic. Tapered pillars meant more floor space in the lower level while still providing adequate support above. By mid-July, he had completed 3 pillars. Each stood 4.5 feet tall, rising from the pit floor to exactly ground level. They looked crude but solid, each one a stack of mortared stones that could easily support several thousand pounds of weight. The second set of 3 pillars went faster because Henrik had refined his technique. He understood which stones worked best at different heights, how much mortar to use, and how long to let each course set before continuing. By the end of July, All 6 pillars stood complete, creating a forest of stone supports inside the excavated rectangle. The joists arrived in sections that Henrik had to assemble himself. He had purchased 12 rough-hewn timbers in Fort Union, each one 16 feet long and 8 inches square. These massive beams would span the width of his structure, resting on the stone pillars and creating the framework for his middle floor. Each timber weighed nearly 200 pounds. Getting them from the trading post to his building site had required hiring a freight wagon, an expense that made the trader assume Henrik was building something substantial. When Henrik explained he was building a cabin, the trader had looked confused but took his money without further questions. Henrik began installing joists in early August. The first challenge was positioning. Each joist needed to rest securely on 2 of his stone pillars while extending slightly beyond them for stability. He had cut mortise pockets into the top of each pillar during construction, small rectangular depressions where the joists would sit. This prevented the beams from rolling or shifting once positioned. But getting 200-pound timbers into place required leverage systems and careful planning. He built a temporary ramp from ground level down into the pit, allowing him to slide joists down on wooden rollers. Once a joist reached the bottom, he used a combination of wooden props and rope pulleys to lift one end onto its pillar. The physical effort was extraordinary. Henrik would position wooden supports under one end of a joist, creating a fulcrum point. Then he would use a long pole as a lever to raise the timber incrementally, adding blocks beneath it each time he gained a few inches of height. When the joist end reached the correct height, he would maneuver it onto the pillar top, then repeat the entire process for the opposite end. Each joist installation took most of a day. He installed them parallel to each other, spacing them exactly 18 inches apart, as he had calculated. Closer spacing would waste lumber. Wider spacing would create a floor that might sag under weight. Once all 12 joists were positioned, Henrik secured them using his iron rods. He drilled holes through each joist where it crossed a pillar, then drove iron rods vertically through the wood and into the mortise pockets in the stone. The rods prevented any lateral movement and locked the entire framework into a rigid structure. This was the innovation that made his design possible. Traditional floor systems relied on joists simply resting on supports held in place by weight and friction. Henrik's system pinned everything together mechanically. An earthquake could shake his structure, and the floor framework would remain solid. By late August, the joist framework was complete. 12 massive timbers spanned the excavated pit, supported by 6 stone pillars, pinned in place with iron rods. The structure looked skeletal, but incredibly strong. Henrik tested it by walking across the joists, bouncing slightly to check for flex. The framework barely moved. He added more weight, stacking supplies on the beams, still solid. The engineering was working exactly as planned. The floor planking took 2 weeks to complete. Henrik used split pine logs, each one hewn flat on both sides, to create boards approximately 3 inches thick and 10 inches wide. He had processed these boards himself during spare time throughout the summer, using a froe and mallet to split logs along their grain, then smoothing the surfaces with a drawn knife. Each board represented hours of work. He needed enough planking to cover the entire 16 by 20-foot area, approximately 320 square feet, of floor surface. He laid the planks perpendicular to the joists, creating a floor that would distribute weight across multiple support beams. Each plank was fitted tightly against the next, with no gaps where heat could escape from the middle level down to the cold storage below. This thermal barrier was critical to his design. The floor had to be solid enough that rising heat would stay in the middle and upper levels rather than warming the lower storage area. He secured each plank using iron nails driven at angles through the board edges into the joists below, a technique called toe nailing that created strong connections invisible from the floor surface. The work required precision because gaps between planks would compromise both structural strength and thermal efficiency. Henrik shaped each board's edges with his draw knife, creating tight fits that required hammering planks into position. By mid-September, he had completed the floor installation. Standing on the solid planking 12 feet above the original ground level felt strange, after months of working in an excavated pit. The lower level beneath him was now an enclosed space, accessible only through an opening he had left in one corner where stairs would eventually descend. The walls for the middle level went up quickly compared to the foundation work. Henrik used traditional log construction, selecting straight pines approximately 12 inches in diameter. He notched them carefully at corners, using a technique he had observed in well-built frontier structures. Each log was stripped of bark, shaped to consistent diameter, and fitted so tightly against the log below that minimal chinking would be needed. The walls rose one log at a time, each one heavy enough that Henrik needed rope pulleys to lift them into position alone. He built the walls 8 feet tall, giving the middle level adequate headroom while leaving space above for the upper sleeping loft. The height was calculated specifically to create proper thermal zones. 8 feet provided comfortable living space while ensuring heat from the fireplace would rise efficiently toward the upper level rather than collecting uselessly against a too-high ceiling. Every dimension in Henrik's design served multiple purposes. Nothing was arbitrary or traditional, simply because that was how cabins had always been built. The fireplace construction began in late September. Henrik built it in one corner of the middle level, using stones he had been collecting all summer. The fireplace was massive by frontier standards, with walls 18 inches thick, made from carefully selected flat stones, mortared together. Thickness was essential for thermal mass. Thin fireplace walls heated quickly but cooled just as fast. Henrik's thick walls would absorb heat during fires and radiate that warmth for hours after flames died down, maintaining temperature stability throughout the day and night. The second floor framework presented different challenges than the first because it had to support less weight, but serve a critical thermal function. Henrik installed joists across the top of his middle-level walls in early October. These beams were smaller than the lower floor joists, only 6 inches square instead of 8, because the upper loft would hold primarily sleeping space and personal items, rather than the heavy furniture and supplies of the middle level. But the spacing was tighter, only 12 inches between joists instead of 18, creating a denser framework. The tighter spacing served thermal purposes more than structural ones. Henrik understood that heat would rise from his middle-level fireplace and press against this ceiling, attempting to escape upward. A loosely constructed ceiling with gaps would allow heat to dissipate too quickly. He needed this barrier to trap rising warmth efficiently while still allowing enough heat transfer to warm the loft above. The solution was solid planking below with calculated air gaps above. The underside of the ceiling would be sealed, tight. The upper side would have controlled spacing that allowed hot air to flow into the loft while preventing cold air from dropping back down. Installing the ceiling planks required working overhead while standing on the middle-level floor. Henrik built a simple scaffolding from scrap lumber, giving himself platforms to work from while handling heavy boards above his head. Each plank was fitted and nailed to the joists from below, creating a smooth ceiling surface for the middle level. He used the same tight-fitting technique as the lower floor, ensuring no gaps existed in the thermal barrier. The work was physically demanding because holding boards overhead while hammering them into position required sustained strength. By mid-October, the ceiling was complete from below. Henrik then climbed up through the opening he had left for stairs and examined the upper side. Here he made modifications to create his thermal transfer system. He left deliberate gaps of approximately 1 inch between every third plank on the upper surface. These gaps would allow rising heat to flow into the loft space while being too narrow for significant heat loss back downward. The hot air would rise through the gaps, fill the loft, and stay trapped there because heat naturally wanted to remain at the highest point in any structure. The physics were simple but effective. Fire burns in middle level. Heat rises and presses against ceiling. Most heat is blocked by solid planking and radiates back down into middle level, keeping that space comfortable. Some heat escapes through calculated gaps and flows into loft. Heat accumulates in loft because it cannot rise further and will not flow downward against its natural tendency. The result would be 3 distinct thermal zones created by careful floor and ceiling construction combined with natural convection principles. Henrik tested the concept on a cold October night by lighting a small fire in his completed fireplace and measuring temperatures. He placed strips of cloth soaked in water at different heights, watching how quickly they dried. The cloth near the fireplace dried in minutes. Cloth at middle-level ceiling height dried in half an hour. Cloth in the loft space above took nearly an hour, but eventually dried completely, proving heat was reaching the upper level and accumulating there. The upper loft walls followed the roofline angle, creating a sleeping chamber with sloped ceilings that would trap rising heat efficiently. Henrik built the walls only 5 feet tall on the lower edge where they met the middle-level ceiling, then angled them upward following the roof pitch he had planned. This created a space with adequate headroom in the center, approximately 6.5 feet at the peak, but lower clearance at the edges. The reduced height served thermal purposes perfectly. Less volume meant heat would concentrate more intensely. A man could sleep comfortably in a 75-degree space even if he had to duck slightly when moving around. Henrik used lighter logs for the loft walls, pines only 8 inches in diameter instead of the 12-inch timbers below. The reduced weight was practical because these logs had to be lifted 16 feet above ground level and positioned on top of the middle-level structure. He built a pulley system using rope threaded through a block attached to a temporary pole extending above the structure. This allowed him to raise logs using mechanical advantage rather than pure strength. Each log still required careful maneuvering once lifted, but the pulley made solo construction possible. The loft walls went up slowly through late October. Henrik worked alone, raising 1 log per day on average. Each log had to be notched to fit the one below while maintaining the correct angle to follow the roofline. The geometry was more complex than the straight vertical walls of the middle level. Henrik made mistakes, cutting notches incorrectly twice and having to start over with new logs. But gradually the loft walls took shape, creating an enclosed triangular space that would become his sleeping chamber. He left one opening in the loft wall for the staircase that would provide access. The opening was positioned above the middle-level stair opening, creating a vertical path from bottom storage through middle living space to upper sleeping loft. Everything connected logically, allowing movement between thermal zones without requiring separate access points. The design was efficient in ways that single-level cabins could never achieve. By early November, the loft walls were complete. Henrik stood inside the enclosed space and felt the difference immediately. Even without a roof yet, the loft stayed noticeably warmer than the middle level below on cold autumn afternoons. Sun heated the logs during the day, and that heat concentrated in the smaller upper space rather than dissipating across a larger area. The thermal concentration effect was working before he had even installed his heating system. Once he added the roof to trap heat and lit fires in the middle-level fireplace, this space would become genuinely warm regardless of outside temperatures. The validation encouraged him after months of skepticism from other trappers. His design was working exactly as planned, and he was only halfway through construction. The staircase system required more engineering thought than any other component because it had to connect 3 levels while remaining lightweight enough not to overload the structure. Henrik calculated that he needed approximately 20 steps total, divided between 2 staircases. The lower stairs would descend from middle level to cold storage, approximately 10 steps covering the 4.5-foot drop. The upper stairs would climb from middle level to loft, another 10 steps rising 8 feet. Each staircase would be steep by modern standards, but acceptable for a man living alone who valued efficiency over comfort. He built the lower staircase first in mid-November. The design was simple but strong, using 2 thick stringers. the angled beams that would support the steps, cut from single logs. He shaped each stringer using an axe and draw knife, creating notches where steps would rest. The stringers were positioned parallel, approximately 3 feet apart, and secured at top and bottom to the floor framework. Steps were thick planks cut to 3-foot lengths and fitted into the stringer notches. No nails were needed because each step rested in its notch, held in place by weight and friction. Testing the lower staircase revealed an immediate problem. The stairs were solid structurally but dangerously steep for carrying supplies up and down. Henrik adjusted the angle by repositioning the bottom of the stringers farther from the wall, reducing the pitch from nearly 60 degrees to approximately 50 degrees. The modification used more floor space but made the stairs practical for actual use. He descended and ascended 20 times, carrying heavy items to verify the design worked under load. The upper staircase presented different challenges because it had to be lighter weight to avoid overloading the middle-level ceiling structure. Henrik used thinner stringers, only 4 inches square compared to the 6-inch stringers below. He positioned this staircase against the wall opposite the lower stairs, creating a layout where someone entering the structure would descend to cold storage or ascend to sleeping loft, depending on their direction, from the middle-level entry door. Each step was carefully shaped and fitted. Henrik worked methodically, checking angles with a simple plumb line and adjusting until each step was level side to side while following the overall staircase angle. The work required precision because uneven steps would be dangerous in darkness or when carrying items. By late November, both staircases were complete and functional. Henrik could move freely between all 3 levels of his structure, experiencing the different thermal zones he had created. The staircases added surprising functionality beyond simple access. They broke up the interior space visually, creating distinct areas within each level rather than single open rooms. The lower level had space on either side of the stairs for different storage purposes. The middle level felt larger because the staircase openings added vertical visual interest. The loft gained character from the staircase entry point. Henrik had built transportation infrastructure that improved the entire structure beyond its practical purpose. The roof went on in early December using traditional frontier techniques Henrik had learned years earlier. He installed ridge poles across the top of the loft walls, then laid split shingles in overlapping rows that would shed water and snow. Over the shingles he added birch bark for additional waterproofing, then covered everything with a layer of sod. The multi-layer roof was heavy but provided excellent insulation. Heat escaping upward from the loft would be slowed by multiple barriers rather than radiating directly into cold air through a single layer of wood. With the roof complete, Henrik's structure was enclosed and weatherproof. He spent 2 weeks finishing interior details in December. He installed a door on the middle level, built shutters for the 2 windows he had included, and constructed simple furniture, a table, chairs, storage shelves. He chinked gaps between logs using a mixture of clay and horsehair that would seal against wind while remaining flexible through temperature changes. Every detail received attention because this structure had to work perfectly or his entire concept would be proven wrong. By late December, Henrik moved his supplies into the completed structure. He organized the lower level as cold storage, stacking preserved meat, bags of dried goods, and other items that benefited from cool temperatures. The middle level became his living space with table, chairs, and workspace near the fireplace. The upper loft held his sleeping platform, extra blankets, and personal items. Everything had logical placement based on thermal zones and usage patterns. Other trappers continued visiting through December and early January, curious to see the finished result of Henrik's obsessive construction project. Their reactions remained skeptical. The structure looked strange with its multiple levels and interior staircases. Douglas visited again in early January and walked through all 3 levels, shaking his head throughout the tour. "You spent 8 months building stairs and floors inside a cabin. Could have built 3 separate cabins in that time." Henrik didn't argue. Words wouldn't convince anyone. Only winter performance would matter. The true test would come during the coldest part of winter when temperatures dropped below zero and stayed there for days. Henrik waited through early January as temperatures gradually decreased. He burned moderate fires in his middle-level fireplace and monitored how heat distributed through the structure. The system was working, but not yet proving itself dramatically because the cold wasn't severe enough. He needed brutal weather to demonstrate what his design could accomplish. The community's skepticism weighed on him, despite his confidence in the engineering. 18 months of work, massive expenses for materials, complete isolation during construction, all based on a theory that most trappers considered foolish. If he was wrong, if the structure failed to perform as designed, he would be remembered as the man who wasted a year building an elaborate joke. The cold arrived seriously in mid-January 1843. Temperatures dropped to 15 degrees below zero and stayed there for 3 days straight. Henrik lit his first significant fire in the middle-level fireplace on the evening of January 14th, exactly 1 year after Olaf had frozen to death. The symbolism wasn't lost on him. He built the fire using seasoned pine and oak, creating steady flames that would burn for hours without requiring constant feeding. Then he began his measurements. He had prepared simple temperature indicators using water in small containers placed at different levels. Water freezes at 32 degrees. By checking which containers froze and which remained liquid, he could determine approximate temperatures throughout his structure. He placed containers in the lower storage level, at floor level, in the middle room, at ceiling height in the middle room, and in 3 locations within the upper loft. Then he waited as the fire burned and heat distributed through his 3-level system. After 2 hours, he checked the results. The lower-level containers had frozen solid, indicating temperatures below 32 degrees. This was exactly what Henrik wanted. The cold storage level was staying cold, despite the fire burning 12 feet above it. The middle-level floor containers remained liquid, but felt cool to touch, suggesting temperatures in the comfortable range of 55 to 60 degrees. The middle-level ceiling containers were warmer, perhaps 65 degrees, showing heat accumulation at the upper portion of that space. The loft containers told the most dramatic story. All 3 remained liquid and felt genuinely warm. Henrik estimated temperatures in the 70 to 75 degree range. He spent that night moving between levels, experiencing the thermal zones he had engineered. The lower storage area was cold enough that his breath formed visible clouds, perfect for preserving meat and keeping supplies from spoiling. The middle level was comfortable for working, warm enough that he didn't need heavy clothing, but cool enough that the fire wasn't overwhelming. The upper loft was warm enough for sleeping without requiring multiple blankets. He lay on his sleeping platform in the loft that night, wearing only a single layer of clothing, comfortable, while a blizzard raged outside and temperatures dropped to 20 below zero. The fire in the middle level had been moderate, nothing like the massive blazes that most trappers burned through winter nights. Henrik estimated he had used 1/3 the firewood that a traditional cabin would require for similar occupancy. The efficiency came from thermal stratification and superior insulation. Heat wasn't escaping through gaps in construction or rising uselessly into empty space. It was being captured in the loft, where it provided maximum benefit for sleeping comfort, while maintaining adequate warmth in the middle level and preserving cold storage capability below. The engineering had worked exactly as planned. 3 distinct temperature zones in one structure, all created by understanding how heat naturally behaved and building a system that exploited those natural tendencies. Henrik fell asleep that night in his 75-degree loft while outside temperatures continued dropping toward 30 below zero. The storm that arrived on January 20th, 1843, became the worst blizzard in trapper memory. Snow began falling before dawn and continued for 36 hours without pause. Wind created drifts that buried smaller structures completely. Temperatures dropped to 35 degrees below zero, cold enough that exposed skin froze in minutes and breathing hurt. Trappers who ventured outside during the storm risked death. Most stayed inside their cabins, burning through their firewood supplies desperately while fighting losing battles against the cold penetrating their structures. Henrik spent the blizzard's first day testing his system's limits. He maintained a moderate fire in his middle-level fireplace, adding wood every few hours, but never creating the massive blazes that emergency conditions usually demanded. He monitored temperatures throughout the structure, using his water containers and by feel. The lower storage level stayed frozen solid, exactly as designed. The middle level remained comfortable despite the howling wind outside. The upper loft maintained temperatures warm enough for sleeping in light clothing. The system was performing flawlessly under extreme conditions. On the storm's second day, Henrik heard desperate pounding on his door. He descended from the loft where he had been resting and opened the middle-level entrance to find William Thorsen, a Norwegian trapper whose cabin was 3 miles distant. Thorsen was hypothermic, shaking uncontrollably, his face showing early signs of frostbite. Henrik pulled him inside and closed the door against the wind. Thorsen stood in the middle level, confused by what he was experiencing. "It's warm," he said through chattering teeth. "How is it warm? My cabin with a fire twice this size is freezing." Henrik helped Thorsen remove his frozen outer clothing and gave him hot coffee heated on the fireplace. As Thorsen warmed, Henrik explained what had happened to his cabin. The fire had been inadequate, despite its size, because the cabin's single level allowed all heat to rise and escape through the roof. The walls had gaps that let wind penetrate. The door fit poorly. Every design flaw that characterized typical frontier construction had combined during extreme cold to create a structure that couldn't maintain survivable temperatures regardless of how much wood burned. Thorsen had realized he would freeze to death before morning and had made the desperate trek through the blizzard to find help. Henrik showed Thorsen the 3-level system, walking him through the lower storage level where temperatures stayed below freezing, then up to the loft where warmth accumulated. Thorsen stood in the loft speechless, feeling 75-degree air, while knowing the temperature outside was 35 below zero. "This changes everything," Thorsen finally said. "Everyone said you were crazy. Everyone laughed. But you built something that actually works." Henrik nodded, but said nothing. The validation felt good, but the real satisfaction came from knowing his engineering had been correct all along. Thorsen stayed 3 days until the storm passed and temperatures moderated enough for safe travel. During that time, 2 more trappers arrived seeking shelter, both having abandoned their own cabins when cold became life-threatening. Henrik's structure housed all of them comfortably, maintaining warm sleeping space in the loft while providing adequate living space below. None of the refugees had believed Henrik's design would work. All of them left as converts. Word spread through the trapping community faster than Henrik had anticipated. By February, trappers were traveling specifically to see his 3-level structure, some coming from 50 miles away. They arrived skeptical and left amazed, experiencing temperature differences that defied their understanding of how cabins worked. Douglas, the Scottish trapper who had mocked Henrik most consistently, arrived in late February with 3 companions. Henrik showed them the same tour he had given others, descending to the cold storage level, demonstrating the comfortable middle level, and finally ascending to the warm loft. Douglas stood in the loft for several minutes, silent, processing what he was experiencing. Finally, he spoke directly to Henrik. "I was wrong. I said you were crazy. I said you were wasting time and money. I was completely wrong." The admission clearly cost Douglas something. He was a proud man who didn't apologize easily, but the evidence was impossible to deny. Henrik's structure maintained 3 distinct temperature zones using a fraction of the firewood that traditional cabins required. The engineering was undeniably superior. The technical questions came rapidly once trappers understood the system actually worked. How deep was the lower level? How were the floors supported? What spacing between joists? How thick were the walls? What mixture for chinking? Henrik answered everything freely, explaining his construction methods and thermal principles without reservation. He wanted others to build similar structures because better engineering meant fewer deaths from cold. Frontier life was dangerous enough without people freezing in poorly designed shelters. Several trappers asked Henrik to help them build similar structures. He agreed to provide advice, but explained he couldn't spend months helping with multiple construction projects. He had his own trap lines to work, but he offered detailed plans, measurements, and explanations of critical techniques. Some trappers copied his design exactly. Others modified it based on their specific needs and available materials. A few attempted simplified versions with only 2 levels instead of 3. All of them incorporated the basic principle that had made Henrik's structure revolutionary, using vertical space to create thermal zones that matched different functional requirements. The phrase Larsen-style cabin began appearing in trapper conversations by March. Henrik never promoted the name, but it stuck because trappers needed a way to distinguish the new multi-level designs from traditional single-room construction. Trading posts started stocking materials specifically for Larsen-style builds, extra joists, additional nails, materials for stone pillar construction. The innovation was spreading organically because it solved a real problem that killed people every winter. Good ideas didn't need marketing campaigns on the frontier. They just needed to work better than existing methods. By spring 1843, 5 trappers within 100 miles of Henrik's location had begun building their own multi-level structures. Some would succeed, others would make mistakes and build poorly. But the concept was no longer experimental. It was proven technology that anyone with adequate skill and determination could replicate. Henrik had changed frontier construction not through formal instruction, but through simple demonstration that better methods existed. The true versatility of Henrik's 3-level system revealed itself during the spring thaw, when stored meat became the critical test. Traditional frontier cabins had no refrigeration beyond winter's natural cold. When temperatures rose above freezing, preserved meat spoiled rapidly unless consumed quickly. Most trappers solved this by smoking or salting meat heavily, methods that preserved food but changed flavor and texture significantly. Henrik's lower storage level offered a different solution that would prove as revolutionary as his heating system. In late March, temperatures outside climbed into the 40s and 50s during daylight hours. Henrik descended to his lower level and found temperatures holding steady in the mid-30s, cold enough to preserve fresh meat without freezing it solid. The earth contact and stone walls that formed his foundation created a thermal mass that resisted temperature changes. While outside air warmed dramatically with spring arrival, the lower level remained cool because the surrounding earth stayed cold from months of winter freeze. The insulation provided by the middle-level floor above prevented warm air from the living space from penetrating downward. Henrik invited William Torsen to examine the lower-level storage in early April. Torsen had returned several times during late winter to study Henrik's construction methods before building his own multi-level cabin. When Torsen descended the stairs and felt the cool air, he understood immediately what this meant for frontier food storage. "You've built a root cellar that doesn't require digging a separate hole," Torsen said, "and it's accessible from inside your living space without going outside." Henrik nodded. The convenience factor was significant but secondary to the preservation capability. They examined meat that Henrik had stored in January. Venison, elk, and beaver meat hung from hooks in the lower level, all of it still fresh enough for consumption. Outside temperatures had been above freezing for a week, yet the meat showed no signs of spoilage. The lower level was functioning as a natural refrigeration chamber, maintaining temperatures that prevented bacterial growth while avoiding the deep freeze that damaged meat texture. Henrik explained that the system should work through most of spring and into early summer before earth temperatures rose enough to compromise cool storage. The food preservation implications were profound for frontier survival. Trappers typically faced feast or famine cycles, gorging when fresh meat was available, and enduring periods of limited nutrition when hunting was poor. Henrik's system allowed food storage that extended significantly beyond winter months, smoothing out the availability cycles that made frontier life precarious. A successful hunt in April could provide meat into June if stored in the lower level. That extended storage meant better nutrition, reduced hunting pressure during vulnerable spring animal breeding seasons, and improved survival odds during lean periods. Torsen spent an afternoon taking measurements and asking questions about the lower-level construction. He wanted to replicate the food storage capability in his own structure. Henrik shared every detail freely, explaining the importance of earth contact, adequate depth below ground level, and thermal barriers between storage and living spaces. The information spread as trappers talked among themselves about what Henrik had accomplished beyond the heating innovation everyone already knew about. Henrik's three-level design spread through the northern Rocky Mountain region over the following 5 years. Not every trapper adopted the method because the construction requirements remained substantial. Building a Larson-style cabin took months instead of days and required skills many trappers lacked, but those who faced the harshest winter conditions or who had lost partners to cold gradually converted to multi-level construction. By 1848, an estimated 32 Larson-style cabins existed across Montana and Wyoming territories. Each one represented lives saved through better engineering. The design evolved as other builders added modifications. Some trappers built two-level structures instead of three, eliminating the below-ground storage to simplify construction, while retaining the warm, sleeping loft concept. Others expanded the lower storage level into full basements with multiple chambers for different storage purposes. A few ambitious builders created four-level structures with separate levels for different activities. The core principle remained constant across all variations, using vertical space to create thermal zones that served different functional requirements. Settlers moving west during the 1850s discovered abandoned Larson-style cabins and recognized their superior construction. Many were reoccupied and maintained by homesteaders who appreciated the thermal efficiency and food storage capabilities. Trading posts and frontier businesses adopted similar designs for their permanent structures. The United States Army built several frontier outposts using multi-level construction after officers noted how well the design performed in harsh climates. The innovation that had seemed ridiculous in 1842 had become standard practice for serious frontier construction by 1860. Henrik himself left trapping in 1849 when beaver populations declined and fur prices collapsed. He moved to Oregon Territory and worked as a carpenter, building homes for settlers arriving via the Oregon Trail. He incorporated thermal stratification principles into many of these structures, though rarely as dramatically as his original three-level cabin. He married in 1851, started a family, and lived quietly until his death in 1876 at age 63. His obituary in the Salem newspaper made no mention of his revolutionary cabin design or the lives saved through his engineering innovation. The original cabin Henrik built in 1842 stood until 1893, when a forest fire destroyed it along with several other abandoned structures. But by then, the design principles had spread far beyond the single building. Frontier construction had evolved to incorporate vertical thermal zones, below-ground food storage, and heat capture systems that transformed winter survival odds. Modern historians estimate that Henrik's innovation directly contributed to saving dozens of lives and indirectly influenced construction practices that improved outcomes for hundreds of frontier families. The story of Henrik Larsson's impossible three-level cabin teaches that revolutionary innovations often come from people solving immediate personal problems, rather than from formal engineering study. A trapper who watched his partner freeze to death created a thermal system that changed frontier architecture across an entire region. His solution required no new materials or complex technology, just existing resources used with intelligence and determination. And that solution shared freely with anyone who asked, became part of the collective wisdom that helped people survive in one of North America's harshest environments. The legacy wasn't carved in stone or written in books. It was built into logs and thermal zones, standing testament to what careful thought could accomplish when applied to fundamental survival challenges.